name is Ander from Tekniker, and I'm here with Themis from LMS. We're happy to present the progress and applications of the OMICRON modular robotic platform for some roadside operations. And in this session, we'll show you how this platform can improve road maintenance tasks, emphasizing in safety and efficiency. So, well, let's start. In OMICRON, we have designed and developed a versatile robotic platform that is able to perform road maintenance tasks safer and in a more efficient way by enabling operators to control the system from the track cabin. It eliminates somehow the need for so many ground personnel in hazardous zones. Our platform supports multiple maintenance operations, such as the installation of cones, the cleaning of road sets, or setting up barriers and signals. And during testing, we target 15 to 20% of reduction in maintenance intervention times, and achieved for some of the operations up to a 100% reduction in personal exposure in ground dangerous zones. So the modular design is central to the platform's adaptability. So it can perform 6 distinct tasks, from pavement crack sealing to removal of lane markings, also cone installations, cleaning of road sets, and setting up safety barriers and traffic signals. We already presented 2 of those operations in the previous External Advisory Board meeting. And today we will focus on the 4 operations that were demonstrated and validated during our final demonstration in Florence. So let's begin with cone installation. So traditionally, workers place cones manually, and that means that they expose themselves to traffic risks. And this platform automates this process, allowing the operators to work safely from inside the track cabin. This solution not only eliminates personal exposure to these hazardous zones, but also reduces the intervention times by 10%. So yeah, we can see it in action with a video that shows the cone installation demonstration that we conducted in Florence. So as you can see, the cones are stored in an orderly manner in a tool that we have in the container. We also designed and manufactured a specialist tool that consists of 3 grippers and suction caps. The system also includes a cone retention mechanism and also has a rear view camera to provide operators with a clear view from the track cabin. The operator can control the system through a tablet interface from inside the track, and this interface allows him or her to configure the initial layout of the cones, and also provides real-time information about the operation. So it enables operators to control when each cone is released. During the process, the operator monitors everything through the interface using this rear view camera I mentioned to ensure proper placement. And this system doesn't just handle the cone placement, but it also automates the cone collection. So for this, the track is driven in reverse, as it is done in current procedures, guided by this rear view camera, from which the track driver aligns the cone with the retention mechanism, and at that point, the robotic arm retrieves the cone. So this entire process is also monitored through this user interface. Okay. Another of the operations that the platform can perform is the cleaning of road signs. So signs usually accumulate dirt, and this makes to reduce their visibility. Traditional cleaning methods also expose workers to traffic risks. And with this platform, we fully automated and controlled from the cabin a high pressure cleaning system, ensuring this way a proper cleaning without risking the workers' safety. So this solution has completely eliminated ground personnel exposure for this task. And this next video shows the demonstration of the roadside cleaning operation. So we have designed a tool to integrate high pressure washer into robot so that it enables to activate and deactivate the system automatically. The setup is composed of a water tank, a pressure washer, cameras for detecting the signs and monitoring the operation, and also an AR interface that allows the operator from the truck cabin to control and monitor the operation. So once the truck is positioned near the target, and the operation begins with the robot approaching the sign. The operator interface also provides some buttons to control manually the robot if needed. And then the system incorporates an automatic detection algorithm to locate the signs. And also alternatively, the operator can manually input the location. And it can also input the geometry of the sign, whether it's circular, rectangular, or triangular, so that with this information, the system calculates the robot's relative positioning and then the trajectories that are needed to clean the surface of the sign. So once the pressure washer is activated, the cleaning process begins, and after completing the task, the robot automatically returns to a predefined homing position, ready for the next operation. And I leave the floor to Themis to explain this video.
Yes, thank you, Ander. So hello, everyone. Good morning. I'm Themis Anastasiou from LMS. So this is the VR teleoperation tool. As you may remember from the previous EAB workshop, this tool enables the operator to control the whole process from within a virtual environment from a safe, distant place. So here we see the environment reconstruction, which is a virtual environment that is reconstructed from the image of the camera that is installed on the platform. So here the operator configures some settings regarding the operation. As you can see, we have some interfaces for displaying information and enabling the operator to trigger different functions from within user interface elements, buttons, etc. So here you can see the real environment reconstructed in this VR view and some virtual assets that have been added to copy the real assets on the road. So here the operation is initialized. The first step, as you can see, is to for the robot to approach the sign. And as you can see, we have some robot holograms showing the future trajectories of the robot, and a clone robot, let's say a virtual copy of the real robot that copies real-time its movements. Here you can see the teleoperation of the robot. So we have some buttons to control the robotic arm manually. and a button to initialize the perception systems to identify the sign. So here the robot approaches the signal at a proper orientation in order to initialize the sealing process. The operator selects the type of the signal, as we saw previously with the tablet application, and initializes the execution of the cleaning process. So this application aims to increase the safety of the whole operation, since the operator is not present on the road, even within the cabin. So the operator is in an office, for example, in a distant place, and the operation is completely automated.
Okay. Thank you, Themis.
Yes, thank you, Ander.
Okay, so another operation that we have implemented is the installation of safety barriers. Installing safety barriers is an operation that is physically demanding and it's a hazardous task. So we have automated this process, reducing both handling and ground personal exposure by 50%. And this innovation, according to our demonstration and validation, also improves efficiency, reducing the installation times by 10%. So here's a demonstration of how this works. So we have a designated area in the container where the safety barriers are stacked, and then we have designed the robot tool to hold the safety barriers, equipped with a joystick that allows the operator to perform the precise movements. Then the truck driver has access to a side camera to assist in the maneuver to correctly position the truck relative to the support post. And then the operator has some AR glasses to perform the operation. Maybe Themis can provide us here some more information.
Yes, so one of the two operators is using an AR headset. So as you can see, we have some visuals, we have some floating panels displaying information for specific manual tasks for the operator. In this step, you can see the operator designate using this hologram a specific position for moving the robot towards the initial position. So this is the first step. As you can see, the robot unloads the safety barrier and approaches it to the two columns we have in order to install the barrier. So you can see some animations and visualizations instruct the operator for performing all these manual tasks. In this step, you can see some sensitive motions using this joystick for manually guiding the barrier. And this is the fastening process where both operators are collaborating to secure the barrier on the columns. Here, the operator moves the robot away from the barrier. And the process is finalized by with a final movement. The robot returns to a home predefined position. And as you can see, the AR interfaces involve some buttons, some UI elements for the operator to trigger specific functions of the robotic platform.
Okay, thank you, Themis. And last but not least, we also implemented another application, which is the installation of temporary traffic signals. So this is also a traditionally labor-intensive and risky operation in which we have automated the loading and unloading of mainly the heavy equipment, reducing this way the personal exposure by 30% and minimizing this physical strain, and ensuring this way a safer and more efficient setups during roadworks. So for this application, we have developed a specific tool that is able to manage or handle signal bases and signal bags according to the Italian elements used in according to the Italian regulation. And then the operator can use these AR glasses again. Themis, please.
Yes, so similar to the safety barrier case, you can see these AR interfaces. In the first step, before initializing the operation, the operator has to calibrate all the visualizations. So for this purpose, as you can see, he or she positions a virtual object, this blue signal you saw. And the first step is for the operator to designate the type of the road asset. So in this case, we have a signal. As Ander mentioned, we have signals, signal bases, and sandbags for securing the bases in a single position. You can see some visualizations also instruct the operator for performing these tasks, and some buttons to trigger the release, the enable or disable of the robotic tool. So you can see this is the unloading process. The operator picks each element and place it on the ground. And then we have the manual process where the operator should install all these assets and create, let's say, the final signal. And here the operator enters the track again in order to move to the next activity area and installs the next sign.
Okay, thank you, Themis. Okay, so to summarize, so the demonstrations and validations of the modular robotic platform developed in OMICRON project have highlighted several key findings. First is feasibility. So our on-site tests confirmed that the platform can perform a variety of maintenance operations effectively, providing this way its practical application in these real-world scenarios. Second is safety. The system significantly reduced the need for ground personnel in hazardous zones, so this makes roadside operations much safer. Third is efficiency. Some tasks such as the cone placement and safety barrier installation were completed with competitive execution time, so showing the platform's potential. Fourth would be ergonomics. So for some other demanding tasks like signal installation, the platform reduces the physical strain on operators, automating the heavy lifting. And finally, accessibility. The AR and VR interfaces makes it quite easy to operate with the system, requiring some minimal training and technical expertise. So looking ahead and with a view towards a future commercialization of this prototype, there are several key steps and considerations that we must address. First is the certification and risk analysis. So to ensure that the system is market ready, we need to conduct comprehensive risk assessments and pursue certifications. This is essential. Second is balancing versatility and specialization. While this platform's flexibility is one of its strengths, we also recognize that focusing on a specific task could allow us for designing optimizations that could improve the performance. And similarly with AR and VR applications, could be tailored further to specific operations, enhancing both the efficiency and safety. And finally, targeting the specific applications. So this system is, well, I would say particularly well suited for small road networks managed by small, medium-sized companies, because it provides somehow an accessible and cost-effective solution for these organizations which often lack resources for more specialized equipment. But this is something to see and to have feedback from you all. So with this, we have reached the end of our presentation.